es Raquel Perales de la Universidad Nacional Autónoma de México en Oaxaca. What am I okay, and the title of our talk is Convergence of Manifolds under Volume Convergence and Uniform Diameter and Tensor Bounds. So welcome, Raquel, and you have more or less between 50 minutes or an hour or whatever you like.
Okay, so I'll check the time. Thank you for the invitation. Well, I'm going to talk about convergence of manifolds. And the convergence that I use, it's called intrinsic flat convergence. This type of distance is very new. So if you have questions about this distance, please ask me. And in the talk, I'm going to tell you about the results and the applications. Then we will talk a little bit about this distance. I will give some history about the problems, and at the end, I'll tell you how to prove the theorems. Okay, so let's start. So here we have our first result. So this is theorem 1. And this is written with Brian Allen from University of Hartford and Christina Sormani from the University of CUNY. And it says the following. So we will start with a manifold M, and this manifold is closed. So that means it's compact and we don't have any boundary. Also, we require this manifold to be oriented, and this orientation is because the distance that we will use requires orientation. So we have this manifold closed oriented, is smooth, and now we have a Riemannian metric on that manifold M. So this G0. This G0 we will think as a fixed metric, and then we will have a sequence of Riemannian metrics Gj. So with this information, our hypotheses are going to be the following ones. We want that G0 is less or equal than Gj. And this just means that if I take a vector V, G0 VV should be less or equal than Gj VV. Then we have this uniform diameter bound, and we require the volumes to converge. So under these assumptions, we will get that our sequence of manifolds Mj, so this Mj is just my manifold M with the Riemannian tensor Gj. So this Mj is going to converge to the fixed manifold M0. And the convergence is with respect to intrinsic flat distance. That's why I have this F here. And this V means that the volume also converges, which we already have here as a hypothesis. But it's important to mention this because the distance that we use do not preserve the volume. What happens is that the volume can drop. Okay.
You mean up to subsequences?
No, actually, with this information, we have the whole sequence. Yeah, we first proved that a subsequence converges, but then we proved that all the subsequences converge to the same M0. So in this case, we don't need subsequences. Yeah.
Wait a second. What if you take just two alternating metrics?
If I take
V1 and V2 that satisfy the condition.
I mean, if I take two alternating metrics, maybe this volume Mj is not.
No, you take the same volume M0.
And the diameter is.
Yeah. There's only two diameters.
Yeah, there is only two diameters, and.
Well, okay. Maybe, are you sure you don't want something like an increasing sequence of metrics?
I mean, this is my increasing sequence of metrics.
No, here it only says that Gj is greater than or equal than G0. Do you need something like that Gj is greater than or equal than Gj minus 1 or something like that?
Okay, maybe in the proof we assume that. Yeah, maybe in the proof. So let me continue and let me think about it.
Sure. Sorry to bother you. Yeah.
Yeah, it's fine. And then the remarks that I have is that this G0 less or equal than Gj just means that the distances between 2 points with respect to dg0 should be smaller than the distance with respect to dgj. And the other remark is that this G0 less or equal than Gj also implies that the volume in the fixed manifold is smaller than the volume in the other manifolds. So actually this limit is actually a limit that is decreasing, or let's say it's monotone, and it converges to volume of M0. And the other remark is that if we have equality in the volume, then these two conditions will imply that the tensors are the same. Okay, so that's in some way the reasoning why we want to get M0 in this limit. Because since the volumes are converging to this, in the limit I could expect to get again M0. So let's continue. So this is our example. And in this example, the fixed manifold is this pink sphere. So here I have the pink sphere, and this bigger space is M1, and then I have M2, and then I have M3. And as you can see, the volumes of M1, M2, and M3 are getting smaller. They are converging to the volume of M0. Also, the diameters are bounded, and because of the figure, the distances in the gray parts are bigger than the distances in the pink manifolds. So this sequence will have an intrinsic flat convergence. I mean, it will converge in intrinsic flat sense, but it won't have Gromov-Hausdorff limit because of these splines appearing here. And there won't be C0 limit of the distance functions. Okay, so let me continue. And the next theorem that I want to present is basically a corollary of the previous theorem, of theorem 1. And in this theorem, we also have this fixed manifold M, but now I allow the manifold to have boundary. So when I say compact, it means with or without boundary. So actually this is with boundary, because I will require the boundary to satisfy the following thing. So I want well, this is not a condition on the boundary. This is actually a condition in the interior. So I want M0 to be totally convex. I mean, to have totally convex interior. So that will mean that any 2 points in the interior will have a geodesic connecting them, and this geodesic has to remain in the interior. Okay, so I have this condition for M0, and then I have the previous 3 conditions on Gj. So this G0 less or equal than Gj, the diameter bound, the volume convergence, and I just add a uniform bound on the volume of the boundaries. Okay, so I add this, and I claim that the same result holds. Okay, this is a corollary, but even though it's a corollary, it was posted in a paper with just Brian Allen and myself, because we realized later on. And this paper with Allen actually has more interesting and more difficult results. So this paper with Allen is just for manifolds with boundary, and we remove the condition of the totally convex interior. We add other conditions. Okay, so let me go on. Okay, so now applications of previous theorems. So there is something called positive mass theorem, and the positive mass theorem was proven by Shane and Yao, and also by Witten in different ways. And it basically says the following, at least the rigidity part. So the rigidity part says that any complete and asymptotically flat Riemannian manifold, Mg, with a non-negative scalar curvature, and ADM mass equal to 0 should be the Euclidean space. And here, just for practical reasons, I'm writing dimension equal to 3. Okay. So since we have this rigidity result, which tells us that something should be Euclidean space, people wonder what happens if you relax the conditions. So relaxing here the conditions will be that we take a sequence of manifolds, so MJ, and they will have, again, non-negative scalar curvature. But now I ask the ADM mass to go to 0. So here ADM mass is going to 0.
Raquel?
Yes?
By equality, do you mean that your space is isometric to E3?
Yes, yes.
So you have some control of the sequence of curvatures with this notion of convergence.
I mean, you get this, I mean, you have this, but then the ADM mass is the one that is going to give you the control on the curvatures and will tell you what is going on. And that's why you will get Euclidean space.
Thank you, thank you.
Yeah.
Raquel, maybe you can explain what's the ADM mass, just to make sure everybody's on board.
Okay, so the ADM mass, I don't know how to explain it. I mean, it's an integral about, you are integrating something related with the scalar curvature, and you are integrating over spheres on your manifold M3. And here I have asymptotically flat, so your manifold actually, it's complete and unbounded. So it's, I mean, think about Euclidean space. That would be very silly because here we want Euclidean space. And we are integrating over spheres. And because we have, and actually we take this limit of integrals over spheres of some expression that is related to your scalar curvature. Yeah, I don't know if that helps. I didn't write any formula here.
Every little helps.
Okay.
Maybe it may be interesting to observe that it's a number.
Yes, it's a number, and it's it should be greater or equal than 0.
And equal to 0 if and only if it's Euclidean.
Yes. Yeah, and that's why it's the rigidity, because you don't know what happens when it's positive, but when it's 0, it should be Euclidean space. Okay. So we are relaxing this condition. I mean, we are allowing our manifolds to have ADM mass positive, but it should converge to 0. And then what we would like to expect is that this sequence of manifolds, well, it should converge to Euclidean space. And in this theorem, what we prove is that, I mean, if we just look at what happens in a cylinder, so this omega j is just, so this PR cross R is a cylinder in Euclidean space of dimension n+1, and we intersect with our manifold. So if we just see what happens in this cylinder, so we will get something that looks like this figure. So this is omega j, and what we are saying is that this part is going to converge in intrinsic flat sense to a ball. So we don't prove that the whole manifold converges to the Euclidean space, because actually this distance, intrinsic flat distance, it's only defined for compact spaces, or we only know what happens when we have compact sequences. So let me, okay, and this paper, sorry, this theorem was proven by Juan Allen-Sormani by a different method, but if we apply the previous theorem, we get a very, very short proof. Okay, and well, there are more results of this type, or of positive mass theorem, or something that is called space-time positive mass theorem. So these results are by Lee-Sormani, Stavros-Sormani, LeFloch-Sormani, and Bryden-Curie-Sormani. So let me move on. And this is our second application. So here again, we have a rigidity statement. So this rigidity statement says that if you have a torus, and if your torus has non-negative scalar curvature, then actually it should be a flat torus. Okay, so from something about non-negative scalar curvature, you get sectional equal to 0. And this was proven by Shane and Zhao and Gromov and Lawson. And so we again ask the same question. What about if we relax the hypothesis? So what we do is we relax this condition, the non-negative scalar curvature. And we say, okay, what about if your scalar curvature is negative, but it converges to 0, because we will take a sequence. Okay? So what we conclude is that then we will have a convergence to this flat torus. Okay, and let me tell you again that using this intrinsic flat distance is important, because if you use Gromov-Hausdorff convergence, there are many counterexamples. So there are a lot of counterexamples that work well with the distance that I'm considering, but don't work well with Gromov-Hausdorff distance. So we have a bigger class of manifolds in which we can relax the non-negative scalar curvature and get again a flat torus. And okay, so the remarks is that here we have this class of tori. And this class of tori was defined kind of copying the class that Huang Li and Sormani gave. So if you think about Huang Li and Sormani, what they are doing is they have something, they have a manifold M, and this manifold M is asymptotically flat. So let's say you can think of something that is like e to the 3 with a different metric. Okay, so you have Euclidean space with a different metric. And now, in this theorem with Cabrera and Pacheco, we have tori. And remember that tori, the universal cover of toris are Euclidean spaces. So basically, the information that they have in their class of manifolds, we are just making the right what? The right identifications. So from the universal cover space of their tori, we get a class of tori. Yeah, I think this is what I should say. And then there is more work about stability of tori, and this has been done by Allen, Hernandez Vasquez, Paris, Pine, and Wang. There is more work because with this class, we are making several choices. So our class doesn't cover all the possible cases, and people would like to prove a stability theorem in a more general way. So this problem is still open. You can come up with a nicer class and try to prove convergence to a flat torus. Okay. So now I'm done with the theorems and the applications, and I would like to talk about the intrinsic flat distance, which is very new. So this distance, if you are familiar with Gromov-Hausdorff distance, then this is going to ring a bell Okay, so this slide is for people that know Gromov-Hausdorff distance. So now you know more or less what we will be doing. So to prove Gromov-Hausdorff distance or intrinsic flat distance, we will do the following. So I start with an M0 and an MJ, and then I isometrically embed these two manifolds in a bigger space set J. And this set J doesn't need to be a manifold, it's just a metric space. Okay, so once that I embed these two manifolds, but isometrically, I can take either their Hausdorff distance or their flat distance in this space. And this is the picture. So I have M, which is this manifold. I have M1, which is this big manifold. Well, a little bit bigger because this is longer than this one. Okay. And the set that I'm choosing here is this type of cylinder. So it's U1 times minus H1, H2. Okay, so now that I have M and M1 in this bigger space, I can take their Hausdorff distance or their flat distance.
Can you remind me what is the flat distance, please?
I'll do that in the next slide, or in two more slides. Okay?
Thank you. Yep.
Yeah. So once that we embed, we could like these flat distances or these Hausdorff distances to converge to zero. And if that happens, we have Gromov-Hausdorff or intrinsic flat convergence. Okay, so let me give more details about this. Okay. So as I told you, this intrinsic flat distance is very, very recent. It was, I think the paper appeared in the archive in 2010, but it was published in 2011. But what we have is the following. So we don't need to have manifolds. We have some things that are more general. And what we have is a metric space, X1, dx1. And the third thing here is a linear functional. I'm not going to say much about this linear functional, but if you have a manifold, of course, here you put the manifold, here you put the distance of your manifold, and here in T1, what you do is integrate top forms over your manifold. So this will be integration of top manifolds. Okay, so if you have a triple like this, or two triples like this, and you want to take their intrinsic flat distance, you need to take this infimum of flat distances of the push forwards. So this is basically why I told you in the other slide that you have to isometric embed, and once that you isometrically embed, you take the distance. Okay, so first we isometrically embed, and then we take flat distance. Okay, and okay, what we have to do is consider all possible spaces Z and consider all possible functions Fi. And let me tell you two things about this. So this is actually not a distance, but this is fine. I mean, if you know about Gromov-Hausdorff distance, Gromov-Hausdorff is not really a distance because you have to quotient out by isometries. So here we quotient out by isometries, as it says here. So two spaces have the same distance, have distance equal to 0 if there is an isometry between them. But you also want to preserve this linear functional that I told you. So the push forward under this isometry has to take T1 to T2. Okay, and then just to compare to Gromov-Hausdorff limits, because maybe you know more about Gromov-Hausdorff limits. So for Gromov-Hausdorff limits, we have that you get the same limit if you assume Ricci bounded below. You also have to assume oriented, because I told you our our definition works with oriented, and your manifolds have to be closed, and your sequence has to be non-collapsed. So in the case that you have Ricci lower bounds, intrinsic flat and Gromov-Hausdorff convergence will tell you the same about the limits. There is no difference. And because of that, well, now people are studying what happens with scalar curvature. Okay, so let me now tell you what is the flat distance. The flat distance, well, we are in a big space set, and here I want to take the flat distance between these two linear functionals. So what I have to do is look for other linear functionals, so this u and this b, and what I want my linear functionals u and b to satisfy is the following equation. So if you think about this equation is actually like Stokes' theorem. So I'm doing Stokes' theorem, and let me explain you with this picture. So in this picture, my first linear functional, this is T1. So here I have a red line that corresponds to T1, and it means integrating one forms over this segment. And then T2 will correspond to integrating one forms over this curvy blue line. And then I have another linear functional, this V, and this V is this thing of 2 dimensions, and it's also integrating over this part. And this green thing will be integrating over these sides, these green sides, okay? So this equation, boundary of V, will give me the red, the green, the blue, and the green. So then I have to take orientations correctly. So then when I add U, I get rid of this one, and I get rid of this side, and then I just get side T2, so the blue one, and the red one. Okay, so any questions?
What was the M on the previous slides? The
M.
black square. Yes, yes.
Yes, M means mass, and in case of manifolds, it's just the volume. So here what I'm adding is the length of this side and this side plus the volume of the yellow part.
Now I see. Thank you.
Yeah, I mean, this is related to a plateau problem. So for plateau problem, you want to minimize volume. So in some sense, we are here minimizing volume. Mm-hmm.
I see. And what is the reason for flat on this nomenclature?
Oh, this is historical, and it was introduced, I think, by Whitney, the one about the Whitney embedding theorem. And at that time, they were using a musical notation. So they had B sharp and another thing. So that's why it's flat.
I see. I see. Thank you.
Yeah.
It's flat as in music, not flat as in curvature equals 0.
Yes, yes, yes.
Yes, I see now. Thank you. Thank you. Thank you both.
All right.
Yeah, okay, and let me explain a little bit more. I mean, to say that, yes, this was used by Federer and Fleming to prove this distance, to prove the plateau problem for integral currents. But their currents, I mean, here I have C, which is a complete metric space. What they actually took is Euclidean space. So this is a generalization of their distance, or of the distance that they used. Mm-hmm. Okay, and now.
Sorry, a question. You have a metric space. It's not a measurement metric space. It's just a metric space.
Yeah, it's just a metric space. Yeah.
Okay.
I mean, actually the measures come from these linear functionals. Yeah, to each linear functional, there corresponds an orientation and a measure.
Okay,
And,
thank you.
Yeah.
Okay, that's clear.
Okay. So now to give you examples about this, so let's start with this first example in which I have I have two manifolds, M0 and MH, and they are equal. Okay, so since they are equal, their intrinsic flat distance is going to be 0 because I told you that if they are isometric and they are oriented in the same way, their distance is going to be 0. But just to practice our definition of intrinsic flat distance, we will do the following. So we construct a space set, and this space set is just a cylinder, so like in this picture. So I have M0 here, and I have MH here, so I already embedded them. And they are embedded by isometrically, they are isometrically embedded. So here they are. Okay, so now I use the definition. The intrinsic flat distance is going to be the infimum of all those things. That's why here I have a less or equal. And then once that I'm here, well, I told you, you should have something of 2 dimensions that is kind of filling in between M0 and MH. So here, so we have this yellow part of 2 dimensions, and then the boundary of this cylinder is going to be, well, the cylinder with nothing inside, and the bottom part and the thin part. So what actually I have to choose as okay, so let's go back to this picture. So what I have to choose as these edges, so this edge and this edge, should be just the boundary M times 0H. Okay, so this is my mass of the thing of 2 dimensions, sorry, of 1 dimension more, plus the mass of this other part. And I know how to calculate this mass. So it's just the volume, and it's H times volume of M plus H times the volume of the boundary of M. So that's very, very easy. Then another example is what about if instead of a cylinder, I mean, if I have N0 that is smaller than NH. So I can construct something that looks like a cone. So this is going to be my set. And in order to calculate the flat distance between these, I mean, I could try to do the same calculations as before, but what is easier to do is the following. So I have one Lipschitz map. So I have a map between this cylinder and this truncated cone. And what happens is that the map that takes this to this decreases the distances. So what we actually have is the following. The distance between N0 and NH is going to be the distance, the flat distance when I embed them. Then here I take again the volume of the yellow part. Here I take the volume of the green part. And now to calculate this, I don't need to know what's the volume of these things. I just calculate using this cylinder. So it's H volume of M plus H volume of boundary M. And that's it. Okay. And now we are ready. Well, we are almost ready to prove our theorem. Okay, so I wanted to mention these examples because in the proofs of our main theorems, we use very similar ideas. Okay, so let's go back to theorems and not about theory of intrinsic flat distance. So several years ago, in 2014, Allen-Sormani. So actually, this is the paper where they proved the stability of the positive mass theorem. So what they used was the following theorem. So in the following theorem, you also have Riemannian tensors. So here Gj, but their conditions are very different. So now look, you have here K2G0, and we have here K1G0. Okay, so actually in our theorem we have this K1J0 less or equal than Gj with K1 equal to 1. And we don't have this condition. Instead of this condition, we have a diameter bound. Okay, so under these conditions, what they show is that they actually have C0 convergence, Gromov-Hausdorff convergence, and intrinsic flat convergence. But even though they have all these three types of convergence, notice that here I write the infinity. So they are not saying that their convergence is to G0. So they have convergence to some space. We don't know which one, to some space. Okay, so they have this theorem. And I mean, just quickly, this theorem was proven using Arcellascoli, because once that you have this, you can use Arcellascoli, so you get a distance, the infinity. And to prove this last part, the flat distance, and also the Gromov-Hausdorff distance, well, you construct a space. And look, this space looks more or less like a cylinder. It's m times an interval, so it's cylinder, but you have to define a distance. It's not, I mean, because mj and m0 have different distances, possibly, the distance is not like the product distance. You have to think about it. But once that you have a distance, you can calculate the Hausdorff distance or the flat distance there, and you get the required estimates to conclude Gromov-Hausdorff or intrinsic flat convergence. Okay. And then Sormani was thinking about this type of theorems. How do we generalize this theorem? And she generalized this theorem with Brian Allen. And notice what they do is the following. So G0 is less or equal than Gj, like in our main theorem. But here, again, they still have this condition. So the K. And what they require is that the volumes converge. So under these two conditions, they again get C0 convergence, Gromov-Hausdorff convergence, and intrinsic flat convergence. And it's an application of the previous theorem. Okay, but, and notice that this looks more and more like in our theorem. In our theorem, the only thing is that we are not going to require this, and we will write a diameter bound, okay? So this is the story, and in order to prove this theorem, they use a very clever idea. So let me tell you what's this clever idea. So this is the clever idea, that if you have G0 less or equal than Gj and the volume converging, then you will know that the distances djk, I mean for a subsequence, you will have that djk converges to D0 almost everywhere. Okay, so this is actually the theorem that helps to prove main theorem 1. This is like the big idea that we took from that paper. Okay, and this theorem also works if your manifold has totally convex interior. I mean, if it has boundary and totally convex interior. Okay, and now let me just finish and tell you how to prove this theorem. Do you have any questions so far? Okay, so let me continue. So we are in the last part of our talk, and I wrote again in the top what is our theorem 1. So we have these tensors, G0 less or equal than Gj, the diameter bound, and the volume convergence, and we want to conclude intrinsic flat convergence. And the proof goes like this. We cannot use Huang, Li, and Sormani because we don't have, I mean, we are not requiring the same hypothesis, and we cannot get from the hypothesis here, we cannot get the right hypothesis. So what we will have to do is construct our spaces set. And actually, this is going to be the picture. So here we have MJ, and here we have M0. And I mean, M0 looks like this because I told you that distances in M0 are smaller than distances in MJ. And we will construct something that looks like a cylinder. So it's this yellow part. So, but what we actually do is we take MJ times an interval. So MJ times an interval is really a cylinder, but then we will glue to it M0. And when we glue it, our cylinder won't be a manifold anymore. And because it's not a manifold, we get these kind of pleated things. I don't know if you see the kind of yellow vertical lines that start at M0 and they go up. Okay, so we won't have a manifold anymore. And in the top part here in MJ, we are actually going to glue another MJ. And what we are doing is we are identifying parts of MJ, which is this red part and this red part we will identify, but there are other parts that we don't identify. And that's why we have these I don't know, semicircles here in the top. Okay, so we need to construct a space set, and there we have to calculate the flat distance. And to calculate the flat distance, well, we just do the trick that I explained before. Okay, so you can compare the volumes of things here with volumes of things here. I mean, it's going to be an upper estimate, but that is fine. Okay, so let me continue. Yeah, let me continue. So here, what I told you is that I'm going to choose some set here. So look here at the red part, and I'm going to choose this set such that this set has very big volume. Okay, so the parts that I want to identify should have very big volume. So this is our theorem. So in our theorem, again, we have our tensors, and we want to say, okay, there is a set W which has big volume, and which has big volume, we just write it this way. So M minus the complement minus W should be very small. This means very small, Vj. That's why it's lowercase v. So we have something that has a very big volume, W, and in this set that has very big volume, we want that the distances are very similar. So here I have that the distance in Gj, I mean, remember, this distance is smaller than the one than G0. But I'm saying, okay, I know that it's big, but it shouldn't be that big. Okay, so I have to write this to delta J. So now that I have this set W, which distances very close, which distances dj and dj0 very close, I construct the space that I told you. So this is the space. So if you look in the middle is a cylinder, and I'm gluing, as I told you, a copy of M0, here it is, and a copy of MJ, here it is. And M0 is just going to become the identity when I identify, so that's easy. And MJ, well, I'm using this set W. Okay, so I'm not identifying all MJ. And okay, this tilde is because I'm doing these identifications. And now I have this appropriate metric. So this appropriate metric just means that if you take 2 points, okay, so you take 2 points in set, and you want to calculate their distance. So what you can do is, because each piece here of set is a manifold, okay, so you can join them by a curve, and then you can divide the curve as the part that lies in the cylinder, the part that lies in M0, and the part that lies in Mj. And there, you know how to calculate the distances or the lengths of curves. So then you take the infimum of the lengths of these curves, and you measure the length of each piece according to where it is. Okay? So then this metric space, you can embed your manifold M0 and Mj, and you can calculate the volume. Okay? So then look at this volume. So in this volume, I mean, it's like a cylinder. This space set is like a cylinder. So here I get the Hj volume of M. Here I get the Hj volume of the boundary, and I get these two. So these two Bj, if we go back, actually come from these blue parts. So this blue part and this blue part and this blue part that I did not identify. Okay. So that's one thing. So because of this theorem, we actually we are almost done with our proof of our main theorem. The only thing that I have to tell you is that how do we get these W's? So that's the last step of the proof. So let me tell you. Okay, here, actually this is what I just explained you, so let me skip it. And this is the lemma in which I'm telling you how to get the W's. Okay. So to construct these W's, what we really use is the almost everywhere convergence of our distance functions. So using this almost everywhere convergence, here really don't pay attention to all these lambdas and kappas. I mean, it's just very technical, but I'm telling you there exists this W, and this W well satisfies what I already told you, that the distances, the dj and the d0 are very, very small. I mean, they are almost the same. So here I have 2 lambda plus 2 delta lambda kj. That is going to go to 0. And also that the volume of this W is going to be big. So that means that the complement has very small volume. So it's going to be this. And this kappa can go to infinity. So this is small. And this part, we have volume convergence. So this part is also going to go to 0. Okay? So this is the lemma in which we tell you, yeah, we have W's. Okay, so this is the goal, find W's. I already told you. And this is the picture. So let me see. Okay, I can finish in 3 minutes. Okay, so this is the picture. I have Mj. Mj is this blue part with these yellow parts. So that's where the distance is big. And M0 is this pink ball. So what I want to get, my W is actually going to be just the blue part. So I will get rid of this yellow part and this yellow part, okay? So then W will have big volume, and then the distance between the blue part and the pink part, it's very similar, okay? So that's what I need to do. Get rid of yellow part. Okay, and this is a little bit technical, but let me go quickly. I mean, I told you, we have the distances converging. So when you have distances converging, you use Egorov's theorem. So by Egorov's theorem, we have an S epsilon in M0 times M0, which has very big volume and where you have actually convergence. I mean, uniform convergence in this smaller set. And now, I mean, this S epsilon is in M0 cross M0, and I want a set in M0, not in the product. So now we have to play a little bit with projections. So we take, so pi1 is projection to the first factor. So here I'm saying that this, because of the volume bound here that I have, well, each projection should also have very big volume. And now, what I'm going to do is I'm going to define these W's as the points whose projections have this amount of volume. So it's big volume. So this W lambda K is the one that works. This W lambda K, I actually can prove that has big volume, as I told you. And because it has big volume, then the complement has very small volume. And these three parts, in order to show that the distance between dj and d0 in this set is very small, we have to play a little bit with Bishop-Gromov volume comparison. And Bishop-Gromov volume comparison, what it's going to tell you is that if you have the projection of if you have SP epsilon, and if you have another SP epsilon, that you can join points in this set with this other set. And this is done using Bishop volume Gromov comparison to say that the intersection between these sets have big volume, it's non-empty, and so you can find points intersecting. And that's why you get 2 lambda here. So you get 1 lambda from here, and this delta kj comes from being in this set and in this set. Okay, and I think, now that we have all the ingredients, I can construct these spaces in which I'm going to isometrically embed my manifold Mj and my manifold M0. And then I use the volume estimate that I told you. So 2 times of these parts that I didn't identify. And then this that corresponds to volume of a cylinder. And then because I did everything very smartly, this hk lambda j, the heights of the cylinders, will converge to this thing. And this lambda, I can take it to 0. So that's very good. I get rid of these 2 things. And then for the other part, I chose them very well. So this volume is also going to go to 0. And that's it. So thank you for your attention. Here's the map.
Thank you very much, Raquel. Would anybody like to ask questions?
Yes, I have one, Paulo.
Please go ahead.
I didn't get it how you prove that theorem about stability of Tori, since you do not have any apparent control under curvatures. How do you can use? Yes, how it's done?
Yeah, so this stability of Tori with the conditions that we impose in the class of manifolds, we are going to get the volume convergence. So when we, and then we will also have the diameter bounds, and the tensors are also going to satisfy DCO less or equal than Tj. So the tensors satisfy this condition because actually we have a flat torus, and then we have a function over this flat torus. And then what we have as Mj is the graph of this function.
Okay, so you don't use explicitly that the bounds on curvature, right?
The bounds on curvature, we use it. Yeah, they are used to calculate the volume because you have a relationship between the ADM mass and the scalar curvature and the volume. So actually what you do is you take the derivative of the volume of the level sets of your function, the function over this flat torus. And when you take this derivative, you get mean curvature. And then, and also you have some part of that you can replace with the scalar curvature. And then this scalar curvature you can replace with ADM mass.
Now I see. Thank you very much.
Yeah.
More questions for our speaker? I actually have a couple of questions myself.
Yeah.
Raquel, can you tell me a little bit about equivariant notions of your, what do you call it, flat convergence, sorry.
Yeah, they are still not developed. Actually, that's something I could like to do. And at the beginning, when my collaborators and I were trying to prove this Tori stability, we use a different method. We use some kind of equivariant method. But at the end, we didn't use it. Actually, if you go to the archive, we have two versions, and the first version is using this equivariant method, but then we found a gap in one part, not in the equivariant part. The equivariant part is fine, but there are not too many things developed. I think our proofs for this equivariant thing only work because our universal cover was very nice. Yeah.
Let's see. So if you have a group acting on by isometries on these manifolds, a fixed group that acts by isometries on all the MJ, do you get an action on the limit?
Do we get an action?
An
Yeah,
isometric-
in this specific case of the stability of Tori, we got that. Yeah.
Okay. There's another question that I wanted to ask you, and this is about the important class of manifolds called almost flat, which you're probably aware of, but there's a very important theory by Gromov, of course. And these manifolds, they are manifolds that admit metrics of arbitrarily small sectional curvature and fixed diameter, say. And usually it is an interesting question to establish whether there exists a limit of the metrics when the sectional curvature goes to 0. Have you ever seen any kind of problem related to this?
No, I think I haven't seen any problem using sectional. We have tried to use a lot of Ricci curvature and scalar curvature. Yeah. Yeah, but I mean, thanks for letting me know. I'll check. Maybe
almost flat manifolds. This is a class of manifolds which is much larger than flat manifolds. And I have been interested in studying limits, Gromov-Hausdorff limits of metrics, almost flat metrics, when the scalar curvature goes to the sectional curvature goes to 0. But Gromov-Hausdorff doesn't seem to be a good notion for the theory, so maybe.
Okay. Yeah. Thanks. I'm going to check that. Yeah, it's interesting.
And finally, I wanted to tell you that I understood why I had doubts at the beginning. I think you're very right. Probably it is true that if you have a metric which is greater than or equal than a second metric, but they have the same volume, then these two metrics must coincide, right?
Yeah.
So now I understand why having a sequence of metrics that is greater than or equal to 0, but the volume tends to the volume of the G0, then the entire sequence, of course, must converge.
Yeah. I mean, it's this theorem that the distances converge almost everywhere. Yeah.
Right. Now I get it. Thank you very much. Would anybody like to ask more questions? Don't be shy.
Perhaps I have a question that is related with what you were about almost flat manifolds. You said that Gromov-Hausdorff doesn't work very well, but what about almost non-negatively curved manifolds? Are you familiar with this concept? Perhaps.
It is probably more general than almost flat, right?
I see. If it's more general,
almost flat is much more restricted. Almost flat is more restricted.
But then this almost non-negatively is also about sectional curvature.
Yes, you have a sequence of matrices with decreasing diameter and increasing sectional curvature. Let's say your sequences have a sectional curvature greater than minus epsilon n,
Yes,
for
yes,
example.
yes, yes.
So I don't know, perhaps studying the limits of this matrix may lead to the construction of some matrix with non-negative sectional curvature.
I see. Okay. Yeah, no, I also wasn't aware of that. Thank you for mentioning this.
Okay, well, if nobody has more questions, we should thank our speaker again. This was a very nice talk. Thank you very much for giving your contribution to our seminar.
Thank you for the invitation.
Thank you.